It is a great pleasure for us to have here with us Yorgos Kordopatis, even remotely. Yorgos completed his PhD studies in 2011. He got his PhD from the Observatoire de Paris. And then he moved for his postdoctoral work first at Cambridge, and then at the Leibniz Institute in Potsdam in Germany. And since 2016, he has been at the Observatoire de la Côte d'Azur at Nice. And he's still there as a staff member today, since 2017. Today, he will talk to us about retrograde stars in the Milky Way, and in particular, their chemodynamical properties. So without further ado, Yorgo, you have the floor.
Thank you very much, and many thanks again for the invitation, and even if it's remotely. So indeed, today I'm going to talk to you about some research of mine that a paper of mine that got accepted a bit more than a month ago about the chemodynamical properties of retrograde stars in the Milky Way. So this is the brief outline of what I'm going to present. First of all, I'm going to talk to you about galactic archaeology. Why do we care about the Milky Way? What kind of data are we looking for and how to interpret it? Then I'm going to dig a bit more into the some recent discoveries done with Gaia about the past accretion events in the Milky Way and how those have been identified and what do we know already about them. And then I will go straight into the core of the topic, the focus on specifically the retrograde stars, explain why do we care about them, and can we say anything about the past accretions just by focusing on them. And I will conclude, and if I have time, I will show you some perspectives on work, ongoing work. So in a lambda CDM universe, it is believed that the structures are growing through the accretion events of smaller satellites. And it is believed also that the Milky Way has been formed like that. And based on simulations, what we see is that the accretion history in the universe is a decreasing function of time. And we can see that around a redshift of 1 or so, you have a sharp decrease of those accretions. And this can be also seen in the simulations from Marie Martig in 2009, where you can see that the majority of the accretions are happening within the first 4 to 5 giga years after the creation of this galaxy. At the same time, observational data from external galaxies have shown that the star formation rate in these galaxies is an increasing function of time up to redshifts of 2 or so, and after, because the gas reservoirs are not filling up as quickly, you have a slow but steady decrease of this star formation rate as a function of time, reaching up to redshift 0. And so what we know about galaxies, therefore, is that their evolution is regulated both by their environment, whether it is gas accretions, accretions of dwarf galaxies that can bring both stars and gas. You can have gaseous migration in the form of filaments, cosmic filaments. But also what regulates the evolution of galaxies are internal mechanisms, such as galactic winds and galactic fountains, which will shuffle the gas content and the stellar yields in different regions in the Milky Way, and will also deplete the galaxies of their gas. You can also have some additional dynamical effects, such as a dynamical heating of stellar populations, either because you have the dwarf galaxy that will hit the galactic disk and make it wobble, or simply because you have a dynamically cold population that is born, and then this will interact with the spiral arms and the central bar, and with time it will increase its velocity dispersion. And you can also have some other effects that I will not be talking in this talk, but I have been working quite a lot during my career, which is called the stellar migration, where in this case you have stars that come into an orbital resonance with the spiral arms and the central bar, and they can move either inwards or outwards without changing their angular momentum. And this shuffles completely the metallicity gradients in these galaxies. So all those events here that I have described shape the influence and the evolution of galaxies. And we aim to understand them. And in order to understand them, we focus specifically in the case of the Milky Way, where we can have very precise information about the stellar motions and the stellar composition. And we focus on the Milky Way, and we survey stars with the aim to derive with the so-called galactic fossils. And those are parameters that are conserved relatively well over time, which will allow us to decipher the history of our galaxy. And I will take you through them. The first type of galactic fossil is, of course, the stellar position and the distances, which first of all will allow us to identify the big structures that is out there, right? The morphology of our Milky Way. And here I'll show you some data coming already from the first data release of Gaia, which is basically star counts, right? So the contrast here is the density, the stellar density. You can see some patterns here, which is basically the scanning law of Gaia. But just by, surveying what's out there, you can already see the main structures of the Milky Way. You have a gaseous disk here, you have a bulge in the middle, you have a thin stellar disk here. You can you can guess a thick disk. You can see some of the Magellanic Clouds, dwarf galaxies. You can see some dwarf spheroidals here. I think this is Carina, this is Sagittarius, and not Sagittarius, Sculptor, and you can see some other globular clusters here. Very interestingly also, you can see stellar streams. And stellar streams are overdensities on the sky that come from disrupted dwarf galaxies that are being accreted as we speak. And perhaps the most famous image is this one of Vasily Belokurov and collaborators back in 2005, which is called the field of streams, where you can see again density plots of the stars in the halo, color-coded by the distance of the stars. And you can see that the most prominent feature here is the so-called Sagittarius stream discovered in 1999 by Rodrigo Ibata and collaborators, which is basically the accretion of the Sagittarius dwarf that's happening as we speak. And this is an artistic view of the accretion of Sagittarius dwarf, which is happening from the other side of the galaxy. The sun is here. And what you can see here, the fork actually, are the leading and trailing tails of the Sagittarius dwarf. And such events, of course, are happening as we speak, not only for the Milky Way, but they are also happening in external galaxies. And I cannot resist to show you this very nice image from a paper of Martinez Delgado in 2010, where you can see here, it's a composite image, but for different external galaxies, you can see these very nice streams orbiting around the host galaxies. So positions of stars can help us to identify the accretion events that are happening as at present, right? And recent accretion events. However, if those accretion events have happened many giga years ago, the stars are completely dispersed in the sky, in the halo. And if you cannot, know where they come from, you cannot distinguish them. This is a simulation coming from the Aquarius suite, where basically you have artificially colored the origin of the different accretion events. And you can see that very, very quickly, the stars are completely mixed between the different accretion events. And if you were an observer, you would see a smooth distribution of the stars on the sky without knowing where they come from. So the question is, how would you be able to identify the different accretion events if you had such a galaxy? And the answer is to obtain the orbits of the stars, therefore obtaining an estimation of the distance of the star, the proper motions, and the radial velocity. And by assuming a galactic potential, you can plot the energy of the stars versus their angular momentum, which are, as we all know by our physics classes, they are conserved quantities over time in a static potential, right? And so by doing so, by obtaining the orbits of all of the stars, or as many stars as you can in the halo, you would be able to see overdensities in that parameter space. And those overdensities are directly linked to stars in the halo that are now completely mixed, and you cannot see them as overdensities on the sky, but you can nevertheless see them as overdensities in energy angular momentum space. So I already presented you the forces of the distances, the positions, and the velocities and orbits. The third extremely important galactic fossil is the chemical composition of the stars. And here, the idea is that the stars of different masses have different lifetimes, and during the lifetime and their death, they are forming different sets of elements due to the fact that different energies are involved into their during their life. And when those stars die, they release in the interstellar medium the elements that they have formed, and those elements can be used later on by the new generations of stars. And therefore, by measuring the abundance patterns in the atmospheres of stars, what you are actually measuring is the star formation history of the region where the star that you are observing has been formed. And here I show you an image made by Shiba Kobayashi earlier this year that shows you a periodic table with all of the different elements, and as a function of cosmic time, here you can imagine that this is cosmic time every time on the x-axis for each element. You can see what the different physical processes contribute to the formation of this element. For example, for calcium, you can see that at the beginning, what contributes the most is the explosion of massive stars, typically supernova type 2, on time scales of few 100 million years. Whereas if you take the case of an element like the iron, what is happening is that iron is mostly formed in a supernova type 1a, explosion of white dwarfs. Okay, and this, you can see it for all the different elements. And so basically what's happening is that because each region of the universe, or if you prefer to narrow it down, each region of the Milky Way and each dwarf galaxy orbiting the Milky Way has its own specific star formation history, the chemical pattern of different elements that you will measure on a star will be a fingerprint on the birthplace of a star, right? And so by investigating, by measuring the chemical abundance of stars and by identifying overdensities in chemical space, you will be able to identify groups of stars that have been formed in similar environments. And to illustrate this, let me show you this very nice plot of Tolstoy, Hill, and Tosi back in 2008, I think, or 9, where you can see the iron abundance of the stars as a function of the ratio of calcium abundance over iron for stars of the Milky Way in gray in the solar neighborhood, and different stars belonging to the dwarf galaxies orbiting around the Milky Way. So here I need to tell you that this scale here is logarithmic and relative to the sun. So basically, a star that has an abundance of 0, it means that it has the same abundance as the sun. And because it's logarithmic, a star that has an iron abundance of -1 has 10 times less iron than the sun. An abundance of -2, it has 100 times less iron than the sun. And so basically what you can see is that the stars that have been formed in different environments here are all occupying different regions in this chemical space. So it's in principle extremely easy to identify stars that have not been formed in the place where we are observing. You can see how well they are different from the typical Milky Way stars. And so in that context, Gaia is a true revolution for galactic archaeology because we are able to, so the second data release, at least that got published back in April 2018, has published the sky positions for more than 1.6 billion stars. You have the colors and the parallaxes for more than 1.3 billion stars. And Gaia has also onboard a spectrograph, which allows to measure the radial velocities for the brightest targets. And so for the moment, 7 million of those have been published. And eventually, you will be able also to get chemical composition for those stars. And this is the aim for the third data release, as I will talk towards the end of my presentation. So the second data release has published extremely important wealth of information for us that has allowed to push forward our knowledge for the Milky Way formation. So here was the situation a bit before Gaia. Here I will be talking about the global kinematics and the extended solar neighborhood in a radius of roughly 2 kiloparsecs around the sun. And so this is a plot that I have taken from a review of Amina Helmi earlier this year, where you can see the so-called tumor diagram, where you plot the azimuthal velocity of the stars, which is the orbital velocity around the center of the Milky Way. And here on the y-axis, you have basically the vertical energy of the stars, which is the quadratic sum of the radial velocity, galactocentric radial velocity of the stars, and the vertical velocity of the stars relative to the galactic plane. And before Gaia, this was what we had. So you could see that you had the bulk of the stars here orbiting at around 220 kilometers per second, which is the value of the local center of rest, which is basically the stellar disk, right? And as you were moving towards lower velocities, you were reaching the halo regime, where you would also increase the vertical energy of the stars. And you would have also some retrograde stars here present. So that was the situation before Gaia. Very soon after the first data release of Gaia, which provided parallaxes and proper motions for the brightest subsample, the group of Vasil Belokurov and collaborators combined the GDR1 data with SDSS data in order to improve the astrometry and go to fainter stars, therefore increasing the volume that was surveyed, for which we had precise astrometry. And they have investigated the kinematics of the stars as a function of Z. Here you see each line are beams in Z from 1 to 3 kiloparsecs, from 3 to 5, and 5 to 7. And as a function of metallicity, in increasing beams going from below minus 2.3, so more than 100 times more metal poor than the sun, up to here a minus 1. And what they have plotted is the radial velocity of the stars as a function of their azimuthal velocity. And what they have identified is that, let's take this panel here, is that you have this bulk of stars here, which rotate at roughly 200 kilometers per second. This is a stellar disk. But you also had this overdensity here, which in this velocity space has the shape of a sausage. And that's why they named this substructure the Gaia sausage, that can be seen down to metallicity of minus 1.7 or so, and up to high distances above the plane. And so this highly radial anisotropic overdensity in the halo, they have associated it to a massive accretion event where the progenitor, given the metallicity of the stars, and when they compared with simulations, should have been of the order of 10 to the 10 solar masses. Few months later, this time using Gaia DR2, Amina Helmi redid the tumor diagram, the equivalent of this one, and saw that what we thought was a smooth distribution of halo stars here actually contained an overdensity. And this overdensity here which was, mostly centered around 0 with a strong retrograde amount of stars, was when, they cross-matched it with ground-based spectroscopic surveys, and they investigated the alpha over iron versus iron plot. They saw that those stars here were also poor in alpha elements, like, you expect from accreted populations like I have shown before. And based on the metallicity range of those stars, and also the fact that they were alpha poor, they have they claim that the progenitor of this accretion event was of the order of 10 to the 8th solar masses. So in both cases, whether it is Gaia sausage or Gaia, this population, it is a massive event. And because they have discovered it with Gaia, and because it was a massive progenitor that for sure must have left some signatures in the kinematics of the disk, making it shake, Amina Elmi and the collaborators dubbed this population as Gaia Enceladus, the son of Gaia that creates quakes, which I find quite a nice name as far as I'm concerned. So regardless of this, in the community, in the two groups at least, people are debating whether Gaia Enceladus and Gaia sausage is the same population. And that's why for people that are not involved in either of those groups, now we call those this accretion event the Gaia sausage Enceladus. And what I forgot to say here, sorry, if you allow me to go back, is that this low alpha population that was confirmed by Amina Elmi was already known back in 2010 by a high-resolution spectroscopic survey of Nissen and Schuster, where they had identified this population here, but because the kinematics were not good back in the day, they could not associate it to a moving group in the halo. So let me go back now to the energy angular momentum space, where now this is a plot taken from Diane Feuillet and collaborators earlier this year, where they have used the Gaia RVS data and combine it with some photometric metallicities in order to do cuts in the energy angular momentum space in different metallicity beams, going from the most metal rich here, going down in metallicities and even lower. And whereas at the high metallicities, you can see these prograde disk stars, when you move towards lower metallicities, you can see this overdensity here appearing from metallicity clearly minus 0.7 up to minus 1.7, which is the Gaia sausage Enceladus population. However, it is rather unclear what is the metallicity distribution of this population. Where does it stop? And you can also see some additional substructures here. And this quest for overdensities in angular momentum energy space have been pushed even forward by several people in the community. And this, now I show you a plot from Naido et al. Again earlier this year, where, so pay attention that the plot compared to this one is inverse. So here you have the retrograde stars and here you have the prograde. But in this plot, it is inverse. The prograde stars are here and the retrograde stars are here. And so this plot very nicely shows all the different suspected overdensities in this parameter space, right? You have the Sagittarius stream here, Sagittarius population that is related to the stream I have shown before. You have the Milky Way thick disk here. You have the Gaia Enceladus here, and you have other overdensities that I will be talking a bit later on. You have so-called Thamnos here. You have another massive event that's suspected and dubbed Sequoia, and you have many of those substructures in the halo. And all of them, as you can see, they are overlapping, and they are not only overlapping in energy angular momentum space, but they are also overlapping in metallicity space, right? It's difficult to say whether they stop or they begin. So this is why the aim of the paper of mine has been to focus specifically on the retrograde stars. And the idea being, the retrograde stars, we know that you cannot form them in situ. You need some external factor, whether you accrete those stars or you take some in situ stars and you make them change their orbit. But in any case, you cannot form in situ retrograde stars. So by investigating them, you necessarily select stars that have been accreted or that are related to accretion events. So the main questions that I have been asking myself were, what can we say about their spatial distribution? Do we see them everywhere? How well are those stars mixed? Can we, just by investigating the properties, identify different subgroups or of accretion events? Are the different accretion events somehow linked between them? And of course, what is their metallicity extent? And in order to answer to that question, I have used, of course, the Gaia data, the astrometry, but more specifically, I have used the ground-based spectroscopic surveys for which we have metallicities and abundances. And those ground-based spectroscopic surveys are listed here. In these summary plots, you can see the resolution of the surveys and the number of targets of those surveys. And namely, you have Lamoste, Segue, and Apogee that observe mostly from the northern hemisphere. You have Rave, Gala, and Gaia observing from the southern hemisphere. And here you have a sketch of the different regions on the sky in the galaxy that they are probing. And here you have a projection in the XY plane, galactocentric. So the galactic center is here, the sun is here, and the color code is the density of those targets. But what I want to stress here is that those surveys are, have a different amount of targets. They are also having different resolutions. They are observing in different wavelength ranges. So it is quite an inhomogeneous sample. And so what I have been using specifically is a catalog published by Sanders and Das in 2018, where they have compiled all of those stars in order to improve the distances of those stars in a Bayesian way by taking into account the metallicity distribution, the colors, etc., not just the parallaxes. And from this sample of more than 2 million stars, I have selected the best subsample, which has small uncertainties in V-phi, smaller than 50 kilometers per second, small uncertainties in parallaxes, less than 10%, and small uncertainties in metallicities, typically FGK stars, because if you are outside this range, it's, I talk from experience, it's quite difficult to parameterize and get a reliable abundance for those stars. And also I have applied some astrometric flags in order to remove potential binaries in our sample. And because I told you that this sample is not homogeneous for the metallicities, it is important to keep in mind the relative fraction of those surveys in the different regions of the galaxy, where basically you can see that Lamoste is dominating will be dominating the star counts at the outskirts of the disk, but Lamoste is a low resolution survey. And towards the inner galaxy, you have all of the Rave, Gala, and some apogee stars here. And when you investigate the metallicity distribution of the different surveys in the solar neighborhood, just to see whether they are all on the same scale, you can see that you have a rough agreement between them. All of them, they are peaking around solar metallicity, or a bit lower as they should, but you don't have an exact agreement between them. So this is something to keep in mind in the way to interpret the results later on. Okay, let's move forward on what can we say about those retrograde stars. So here I'll show you again the tumor diagram that I have shown before, and this is for my sample. And you have the retrograde stars here, and you have the prograde stars here. When you investigate their HR diagram, or in particular their TF log G diagram, color-coded as a function of V phi, you can see, well, of course, for the prograde stars, you have a wide range of parameter space, which reflects the wide range in metallicis and ages. And this range is much limited when you investigate the retrograde stars. However, it's not, a single age population. We know that the retrograde stars have a range in metallicis, as I have shown you, but this range, this width that you see in the turn-off region in the giant branch, it cannot be only explained by a range in metallicis. It means that the retrograde stars that you have in your halo are not a mono-age population, basically. Okay, and so this is the first thing that we can directly infer from this plot. Okay, let's move forward now and see how the metallistic gradients of the stars are. What can we measure? So let me just again guide you through with the prograde stars first. So here you can see the mean metallicity of the stars as a function of radius. Okay, for stars close to the galactic plane between 0.2 and 1 kiloparsecs, then you move higher up from 1 to 2 kiloparsecs above the plane, and then even higher up between 2 and 4.5 kiloparsecs. So you can see that for the prograde stars, you have a negative gradient here, which was already known since a long time. And as you move higher up above the plane, this gradient flattens and eventually even reverses at high distance above the plane. And this is also something that we knew already from, I think, 2013, based on RAVE data, where basically what is happening here is that we suspect that the thick disk is more radially concentrated than the thin disk, sorry, and that the thin disk at the outskirts flares. So basically, if you are here and you measure the radial gradient, you start from a metal poor population, and then eventually you start in probing the more metal-rich thin disk that has flared and that had reached high distance above the plane. And this is what you see here. You have an increase in the metallicity. Okay, you can also measure the vertical metallicity gradient at different radii this time here, and you can see that at the outskirts you have some differences here in the vertical gradient, but I will not spend more time in that. All those things were relatively known from the past, but this is, a sanity check that what we're doing is correct. So, okay, this is for the prograde stars. You can see that there's an evolution. Let's now see what's happening for the retrograde stars, okay? And this is what we see. So you see that the gradients are different than for the prograde stars, whether it is the radial gradient or the vertical gradient, and that they do not change as a function of Z here or as a function of R here. So you have obviously a shift here that is a reflection of this vertical gradient here. But what you see basically is that the gradient is the same, and that the retrograde stars in our sample do not show strong variations of the metallicity gradients, and that therefore that it is the first hint, and we will see later on, that it is a well-mixed population, right? In the probed volume, you cannot see any dramatic differences in the way the metallicities are distributed. And very briefly here, as a sanity check, I have broken my sample into surveys just to make sure that I have an homogeneous sample and that this result is not coming from the inhomogeneity of the metallicities. And you can see here that whereas for the different color codes here are associated to the different surveys. And here I show you the way, for example, the radial metallicity gradient for the prograde stars changes as a function of Z. And you can see that all of the surveys show the same trend, flattening and an inversion of the metallicity. And for the retrograde stars, you can see that, all of the surveys show the same trend, basically zero change in the metallicity gradients. And this regardless of the surveys. So you have some noise because now each point contains less stars, but basically this is the main answer, that even when you take a subsample associated to one survey exclusively, the results do not change. Okay, so now we'll combine the chemistry with the kinematics in order to see if I can say something more about those retrograde stars. So the fact here is that the kinematics, as I told you, give you information on the dynamics of the population, and the chemistry on the star formation history of the population, right? And but because the different distribution functions, if you take them independently, whether it is velocity or chemistry, they can be overlapping, it is quite difficult to say anything if you take them independently. So the idea here is to investigate the correlation between the kinematics and the metallicities to say anything about the retrograde stars. And here is my sample here overall, where I show you V phi, the azimuthal velocity, as a function of metallicity, color-coded as a function of their position in the galaxy. And these are the retrograde stars in my sample. Here are the error bars in the metallicities that you can see what they are. And here, believe me, there are some vertical error bars, which are the uncertainties in my velocities. So I have very small uncertainties in my velocities. And you can see already some trends here that I will be discussing in the next slides. Okay, let me guide you through again here. So I start in the solar neighborhood here, and I take the prograde stars and investigate the way V phi changes as a function of metallicity. Yes. And so here you can see the local standard of rest at 240. Here you can see the solar metallicity just to guide the eye. And you can see several trends here on the prograde stars that are more or less already known. First of all, for the faster stars, which is basically the thin disk regime, you can see a negative correlation between the metallicity and V phi, which is basically something that has been already suggested by Lindenbellen and Kalnas back in 1972, which is basically due to the velocity dispersion of the stars combined with the metallicity gradient in the disk. And what is happening is that you have the metal poor stars basically belonging to the outer disk that are entering your volume at their, and therefore at their pericenter, and they are therefore going faster than the local center of rest. Those are those stars here. And you have more metal-rich stars that belong in the inner disk, but because of their eccentricity are entering in your volume here. And because they are at their apocenter, they are going slower than the local center of rest. And this is what you see here. So this is quite a known phenomenon. When you move towards lower velocities, where the thick disk dominates, you see that you have a positive correlation, which origin is unknown, and it can be indications of either an inside-out formation of the thick disk or a cloud collapse or of superpositions of mono-age population. So this is a quite complicated topic. I will not enter into details. But this is also something that has been discovered back in 2010 by works of Alessandro Spagna and some work of mine during my PhD thesis. What is interesting here, and we had not seen back in the day, but is relative to the topic that I'm discussing today, is that this correlation between V phi and metallicity flattens as one moves higher above the plane. And apologies, I just realized that I have not explained what are the different colors here. The different colors are distances above the plane. So, right, I'm here in the solar neighborhood, and I am probing different distances above the plane. The blue is close to the plane, and the more yellowish you are, the more you are above the plane, eventually here being more than 5 kiloparsecs above the plane. And what you can see is that this correlation flattens and even possibly reverses at high distance above the plane, which can be an indication of a co-formation of the galactic thick disk and of the inner halo. And this has been suggested from a long time already, but more intensively since the advent of Gaia DR2 by several works such as Haywood and collaborators, Gallard et al. Or Kolov et al. So, okay, this was the result for the solar neighborhood. What can we say now if you go inwards and outwards? Very quickly, you can see roughly the same trends still for the prograde stars, right? You have this negative trend for the rapid stars, then a negative trend everywhere. So the only thing that changes is this inflection point going towards higher velocities in the inner disk and lower velocities in the outer disk, and the lower metallicity in the outer disk and high metallicity in the inner disk. But globally, the trends are the same. So we understand what's happening, let's say. Now let's focus on the retrograde stars. And this is what we obtain. So you can see that you have only a single regime here, regardless of the distance above the plane, okay? And regardless also of whether you are in the inner disk, the solar neighborhood, or the outer disk, okay? So you can see a shift here, okay, which is related to the vertical metallicity gradient that I have mentioned before. But basically, you see that there's only one regime. And so this tells us two things. First of all, as I told you, that there's no change in the trends as a function of R or Z for the retrograde stars, and that therefore those are, again, a well-mixed population. But also this tells you that within the probed volume, you have no orbital turning points for the different potential subpopulations that you have. This means you don't have shells in your accreted subpopulations that could make a change here in, you know, in the velocities and or the metallicity that would change the regime of this correlation. So within the volume where we are, which is, I should have noted it, but I think it's between 5 to 10 kiloparsecs in R, and again, 0 to, minus 7 to plus 7 kiloparsecs above the plane, the retrograde populations is perfectly well mixed. So we cannot say much here. It is interesting already what we said, but we cannot say much more. So we need to go a bit more into a classical approach, selecting now stars in regions in the velocity space. So I buried myself in this plot of Koppelman and collaborators in 2019, which shows the tumor diagram here again. And you can see here identification of the Gaia Enceladus, the Sequoia accretion event that I have briefly mentioned before, and Thamnos here. And so basically I made some boxes in my sample, where here you have a population that will mostly probe the Gaia sausage Enceladus, then at the same V5 range, a sample that would probe the Thamnos population, and another large selection in the lower V5s, which I call others, but contains in particular the Sequoia accreted event. And now investigate here now, without cutting in R or Z, the metallicity gradients of those different subgroups. And you can see for Thamnos, this is the gradient that you see, this is for the Gaia sausage Enceladus, and this is for the other subsample. You can see that those three subpopulations show similar gradients, but you know, not the same metallicities. And whereas you would expect that those stars and those stars do not have the same metallicity, because you know, you have a correlation between V5 and metallicity here. However, for stars between the ones probing Gaia sausage Enceladus and Thamnos, which are at the same V5, you would not expect such a shift in the metallicities. And I will come back to that later on. But what we can say already from those negative metallicity gradients is that those are compatible with an inner metallicity gradient in the progenitor. Let me pause here and explain a bit in hand-waving way how things would happen. So let's imagine that you have a massive progenitor, and in the potential well of this massive progenitor, you would keep, you know, the yields of the different stellar populations, and you would increase with time your metallicity. Okay, and because it is a massive progenitor, what would happen is that you would have an inner metallicity gradient. The outskirts of your dwarf galaxy would be more metal poor than the core of the dwarf galaxy. And once you have this progenitor that would fall into the galactic potential well, it would, you know, strip first the outskirts, the most metal poor, that would be on high eccentric orbits, and eventually you would have towards the end, the accretion, the dilution of the core, right, at the low z's. So this is what you see at the high z's, in principle high eccentricities, you have lower metallicities than here. So what time is it? Yeah, okay, I'm just a bit over time. Let me go very briefly now. What I have investigated is that the way the metallicity changes as a function of the eccentricity for those stars, because what intrigued me is that this sample and this sample, whereas they have the same V-phi distribution, they have completely different kinematics, metallicities. And what you see here is that the Thamnos probing population and the Gaia Sausage Enceladus probing population follow a very similar trend in metallicity versus eccentricity, which is quite suspicious. Okay, it is suspicious that it would tell you, okay, well, you have contamination in Thamnos coming from Gaia Sausage Enceladus. Okay, and you can already see it from this plot. It's not a clean selection. It can also be the fact that I'm not probing the entire Gaia Sausage Enceladus population. You have some prograde stars here that I am not selecting. However, it can also mean, and you cannot exclude the fact that these two populations are linked, right? You know that you have more stuff than just Gaia Sausage Enceladus here. And so these are linked, presumably. And if they are linked, how and why do you have the more metal-rich population being on more eccentric orbits than the more metal-poor population? Which is counterintuitive to the argument that I have said before, where you first accrete the outskirts of a massive progenitor on high eccentricities, and you end up with accreting the core of the progenitor on lower eccentricities. So this is clearly an open question. And so these, I will stop here. I have one slide after with the perspectives, but these are my conclusions about the retrograde stars. In the volume that I probed, they are a very well mixed population, right? And then if you want to say something more about them, you need to go in more outskirts, farther radii, where, you know, probing RL, IRA, etc. What is extremely advantageous is that in December this year, you have the early data release of Gaia that will arrive with better astrometry and parallaxes, but no new radial velocities or chemistry. But nevertheless, we will be able to say more about those stars. The interesting stuff will also come in 2022 with the global Gaia data release 3, where you will have radial velocities for several tens of millions of stars and chemistry coming from spectroscopy. And already starting from next year, you will have ground-based follow-ups of Gaia targets coming from WIV and from Foremost in 2023 that will obtain high-resolution spectra for the bright targets of Gaia, which will allow to have eventually velocities with a precision of a few hundred meters per second, and also individual abundances with very good precision for coming from more than tens of elements. And you will also have low resolution spectra for the faintest targets for which Gaia will not provide radial velocities. And very briefly, let me also point you and open the discussion to something that I have highlighted during my works, which are the super metal-rich retrograde stars. And these are extremely puzzling stars because, as I told you, retrograde stars cannot be formed locally in principle. And also stars that have a metallicity above solar, we don't know, the only place we know that those kind of stars are formed are in the inner galaxy, the inner Milky Way, because you need an intense star formation history that will enrich the metallicity of the stars very rapidly. And so the fact that you have a retrograde super metal-rich stars is extremely puzzling. So what I have investigated is whether those stars have suspicious parameters. However, the spectra of those stars are good. You see that they don't have much noise. The spectra are in black, and you can see in red the models that will fit on them in order to derive the metallicities. And what I am doing at the moment is I am integrating their orbits in order to see whether you can say anything about their origin, whether those have been indeed stars formed in an external galaxy that has been accreted, which sounds very suspicious, or those are stars from the bar. This would explain a lot, or stars that have gained retrograde motion after an accretion event, which is also something interesting that will tell us a lot about the dynamics of this massive accretion, which is associated to the Gaia sausage Enceladus. Thank you very much.
Thank you, Yorgo. Thank you very much for this very interesting talk. Do we have any questions for Yorgo? You can just unmute your mic and ask.
Can I ask one or two, Vaso?
Of course.
Okay.
Go ahead, Nico.
Nikos Skilafis. These streams that you showed, just to make sure, are they from interactions of galaxies like the antenna that we see such streams? Are all these streams coming from interactions with external, smaller or larger galaxies?
Exactly.
They are, okay.
So yes, so
that's what I thought, but that's fine. Okay.
Yeah,
now,
but what I want to precise is that those accreted satellites are, for the moment, the ones that we see, of extremely small mass, right? The mass ratio is very low. It's not 1 to 4, not even 1 to 4 as Gaia sausage Enceladus would be. And also you can see some streams of disrupted globular clusters that we know also exists in the halo.
Okay, very interesting work. I was not aware of, I'm not doing stellar astrophysics, so very interesting. It seems to me quite difficult to solve the inverse problem, namely from what you see today to find a unique solution in the past. It's a multi-valued problem, isn't it? So you will make some inferences about the past, but not in a unique way. Is that correct?
That's correct. Is that your question? Because yeah. I have a comment on that. Yeah, so that's very correct. That's very accurate. That's spot on. What helps a lot, and I have not discussed at all here, is the stellar age. And this field of stellar age determination now is advancing very rapidly since a decade now, where you can obtain very precise ages coming from astroseismology. For the moment, this is limited on relatively bright stars and giant stars, but also using Gaia astrometry, now you are able to put on an HR diagram quite accurately the stars. You can know, their color and their absolute magnitude, and you can fit isochrones from that. And therefore, you can have a relatively good idea of the age of the stars. So once you have the orbits, energy and angular momentum that is conserved over time, once you have the chemical composition that is also conserved over time, and you stick on that, the age, then you have everything in hand in order to rewind time and make a coherent story of what you're seeing. But of course, there will always be degeneracies in all this.
Oh, yeah, the age will help a lot. Yes, I understand. Thank you.
More questions for Yorgo?
Let me add that, the things that I am doing now about the orbital integration of those stars, this is a very, I explore for the moment, and it depends a lot. I have not explained here because I do not have time, but it depends a lot on the galactic potential that you assume, on the way the galactic potential changes over time, which we know is changing. And those assumptions now are, the most basic as they could be. So, there are still many, many open questions on this topic.
One more question, Vasha?
Vasilis has a question.
Okay.
Vasily.
Yeah. Vasily, go ahead, Vasily.
No, very nice talk, Yorgo. Just to understand, a lot of the analysis that you did, you plot V phi, right?
Yeah.
But that, in a sense, depends a bit on the model of the galaxy, right? In order to infer that, is this directly measured quantity?
Yes. So V phi is indeed a direct measured quantity. It's basically the combination of the distance and the proper motions and the radial velocity.
Okay, so
you need to assume a distance to the galactic center, basically, and you need to assume the solar motion. And on the other hand, the energy, that you obtain it by assuming the galactic potential. So it's a level 2 product, if you want.
Okay, yeah, thanks. Then also you suggested that in order to identify the different populations per se, right? You had energy and angular momentum.
Yes.
And I was wondering if you have dwarf ellipticals that go through the galactic disk, they will progressively lose their stars, right? And as they oscillate per se in the galactic potential, the stars that they will lose will have effectively different energy, right? Because they lose them at a different, the early work that Queen, etc. did. So when you identify this sort of like lossy on this plane, is this taken into account when you identify the different areas, say Thamnos and so on?
Yeah.
Or do you see events, major events during which a bulk of sort of like stars were ripped apart from the intruder per se?
Yeah. So it all depends on the dynamical friction that the stars will experience.
Right.
When you have a stellar stream, for example, where you physically tear apart a dwarf galaxy, this dwarf galaxy will remain coherent in energy angular momentum. You will have a small dispersion over time, but it will remain a coherent structure in energy angular momentum. Now, if those stars sink into the galactic plane and start by dynamical friction gain a smooth, let's say, disky orbit, this will change. Yes, clearly you will see it in the energy angular momentum. The energy will not be conserved anymore.
Thank you.
Yeah.
Nico, you had another question?
Yeah. Again, because this shows my ignorance, Yorgo.
Sure.
Am I right to assume that all or nearly all stars start prograde motions and then with interactions change slowly into retrograde? How do retrograde orbits come about?
Exactly. So at least my understanding of things, and I think this is the understanding of a lot of people, is that, you know, let's assume now that you have a disk galaxy. The way to form stars, right, is that you form stars from the gas that exists there. And the gas follows the general motion of the disk. And everything is prograde by definition. So the new stars that you will form are also prograde. They will orbit with, in the case of the Milky Way, 200 kilometers per second, if you are roughly at the solar neighborhood. Now, what's happening is that with time, you will increase the velocity dispersion of your population. You will start dynamically cold. All of the stars, let's say, will have the same velocity. And over time, because you will interact with the giant molecular clouds or the spiral arms, the velocity dispersion will, you know, open. And however, you will still remain, you know, the dispersion will increase by up to 20, 30 kilometers per second, up to 50, let's say. You will never go from 220 kilometers per second prograde motions to 0 or even negative. You cannot go negative in principle. So in order to be negative, it is only stars that have been accreted, and that have been accreted on specifically retrograde or nearly polar direction. Okay, and what I want to investigate now with simulations basically is whether when you have such a retrograde accretion that will bring retrograde stars, whether you can take with you some in situ born prograde stars and change their motion, or if you take with you some gas and you change its motion to become retrograde and therefore form there afterwards some retrograde in situ born stars. And that's, I think, is what the supersolar metallicity retrograde stars will tell us, whether this thing is possible. But I would like to confirm it with the simulations also.
Okay, thank you.
So Yorgo, I was going to ask something very relevant to what you just said about the supersolar retrograde stars and the possibility that they were basically dragged along by some merger event. So you mentioned that you want to study this with simulations. My question was going to be, has it been studied at all before? So do we have any sense about the likelihood of such events already? Or this is a completely new field and you're going to look at it now?
To my knowledge, this has not been investigated before. And this is for several reasons. Those objects here are very few. If I show you here again this plot, you have very few of those stars. Here you see the contour lines. And overall, from my let's say my 2 million initial sample, I have 100, even less if you try to be conservative, of those supersolar metallicity retrograde stars. So these stars is noise among all of the other things, but I think that's, the devil is hidden in details, and I think this is something that's worth pursuing and investigating in simulations. And also, sorry, this has not been investigated because chemical information in simulations is something that is relatively recent also.
Thank you. Do we have anything else for yours? Any other questions? Anybody? Okay, if not, let us thank Yorgos very, very much again for this very interesting talk, and hopefully we can discuss more and have you here in person once the difficulties with COVID are over. Thank you, Yorgo. Thank you.
Bye.